give some damage, and then we give the loading. We will have the crack at the bottom. Yes, I will explain in the next slide. Anyway, in this study, we use the HPLCC, and I selected one of the HPLCC called ECC, developed by Victor Lee in Michigan University. Anyway, the material today I talk is on the ECC, one of the HPLCC. So for experiment, we prepare two types of plate, very thin plate, 2 centimeter thickness. The size is, one is 40 centimeter and 25 centimeter for the standard test, for the control plate, we call it. And for main plate, a little bit bigger one we prepared, but still the thickness is 2 centimeter and size is like 50 centimeter and so on. Anyway, it's not so big. So to this one, we apply the bending. For the control specimen, we just apply the 4-point bending to check the deformation or multiple cracking and so on. So for the control, for the main plate, yes, we firstly give the bending to a certain degree of damage. Then after that, yes, we unload. Yes, we have the cracking on the bottom surface because of the bending. Then we finish once, we stop once, and flip and make it flat. And then it's a unique thing. We cut to a certain degree the specimen with some damage due to the initial loading. And then this size is same as the control one. And yes, we do the same bending test as the control one, but with initial damage with certain angle. So we have selected 4 types of degrees of the inclination of the initial damage. So then firstly we give the initial crack, and then we apply the load. So that situation represents the tensile test with some damage with a certain angle, like 20 degrees, 70 degrees, 45 degrees, 19 degrees, and so on. Then we can check how the initial cracking slide after the cracking. So I show you the load displacement curve of the bending test of the plate with initial damage with 20 degrees cracking, initial crack, 45, 70, 90s. So many lines on it, but this white line is non-damaged case. And this colored line are the result of the with damage. So for example, when we see the 20 degrees, we see the reduction of the stiffness, right? From white one to yellow one, but we do not see so much on the strength. Similar strength is observed. But by increasing the angle from 20 to 45, yes, initial stiffness decreases a little bit, and strength also decreases a little bit. And yes, 70 also. But in case of 70, the reduction is less on the initial stiffness, but still the strength reduces. And for 90 degrees, we have almost no reduction of the stiffness, and still we have the strength reduction. So due to the initial damage angle, the secondary loading result changes dramatically. So it's because of the initial damage that may relate to the shear performance of the initial cracking. So this slide summarizes the strength reduction ratio and initial stiffness reduction ratio against the pre-crack orientations. For 20 degrees, we do not have we do not have the strength reduction, but increasing the angle, yes, we have a reduction, and for 90, a little bit recovered. And initial stiffness, yes, 20 degrees decrease more and recovered like this. So why this kind of phenomena happens can be explained by the detailed investigation of the phenomena. So let's look at the cracking pattern. So we use some special powder and give some black light in the very dark room, then we can check the cracking after the test. So this is the initial loading result. This is the main plate, and we give just a bending load, and we have the multiple cracking. This is a feature of the HPLCC that shows a good ductility. And after that, yes, in the test, we cut the plate like this. And then again, yes, apply the load, but different direction. So then we will have the secondary crack like this. So we can change the principal stress direction from this direction. First one is yellow one, and second one is red one. So this is the experimental scheme. So this is a result of the cracking pattern after the secondary loading. Actually, we give two types of loading level, 40% or 70%, but it doesn't matter so much. Anyway, the 20 degrees, 45 degrees, 70 degrees. So yellow line is pre-crack, means the initial loading, and this dot yellow line shows the initial cracking direction, and red one is secondary principal direction, means first damage and second loading. So when we follow just we think this is just a homogeneous or isotropic material, secondary crack should follow perpendicular to this principal stress line. Means, yes, in this slide, horizontal crack should occur. However, we do not have the secondary crack tend to occur perpendicular to the initial cracking direction. It does not follow the secondary principal stress direction. For example, let's see this one, 45 degrees case. The initial secondary crack should have to this direction, but we do not see so much the direction, the crack with this direction, but almost normal, means the perpendicular to the initial direction. It is because this material becomes an isotropic material because of the initial damage, and that is caused by the weak shear transfer of the first cracking. First cracking slide easily, then yes, this field becomes anisotropic. Then yes, unexpected secondary crack occurs. So this is a scenario of the secondary crack. So by the way, when we use the just concrete, normal concrete with aggregate, we don't have this kind of problem. Actually, we haven't seen this kind of phenomena in normal concrete because we have an aggregate in concrete. When we have an aggregate in concrete, or even if we have an initial cracking, because of the good shear resistance, the secondary crack occurs following the secondary principal direction. But when we have very weak shear performance, the sliding will become very easy. So then, yes, unexpected secondary crack is generated. This is what we found in this research. So that was the case of some with 20, 45, 70 degrees. And in case of 19 degrees, we don't have any shear sliding because initial crack is perpendicular to the secondary principal loading direction. But we still have the reduction of the strength a little bit, 10%. Probably it is because due to, yes, this is the secondary loading direction, and this is the initial cracking. Probably yes, it is because of the crack, initial crack. In the vicinity of the crack, fiber does not work well. That causes about 10% reduction in the strength. Anyway, we did the test and to check how it reduces. So this is a cracking pattern. As we see in this case, yes, we have the orthogonal cracking when we give 19 degrees crack. So anyway, from the plate experiment newly proposed, very simple bending, yes, we could confirm the reduction of the strength by due to the initial damage with a certain angle, and we could summarize. And also cracking patterns was also checked. So based on the experimental result, we try to make a model in shear. So actually, it's not so easy. But finally, we developed, and this developed new model is incorporated into the normal the simulation program, FEM simulation program called COM3, developed by the University of Tokyo. That is for the just reinforced concrete, not HPLCC. But based on the normal concrete constitutive model, stress-strain relationship, yes, we modify for the HPLCC. This is a general view of the COM3 constitutive model. We have a constitutive model for compression, tension, and shear. And also RC means how it behaves when it is used in the concrete is used with reinforcement. And we adapt the multidirectional fixed cracking model. I mean, all the crack is presented in the simulation. But anyway, this is well developed model, and this program has been contributed to evaluate the performance of the structure. Especially in Japan, we have many earthquakes. We need to know the capacity of the structure and seismic performance and so on. This kind of thing can be done in this program. So to this program, yes, we introduce or incorporate, we introduce the new model. So firstly, in compression. For compression, it's not so difficult. This is the original COM3 model, but it is known that HPLCC or ECC used in this study shows less stiffness and have a higher peak strain. So based on the experiment, we modify, and same unloading reloading curve is adapted. Yes, in compression, the modeling is not so complex, and we checked the model, and yes, compared with the experiment, then it's okay. And also, due to the lateral damage, in compression also we have some reduction of the strength. So this is model using some previous researches. Anyway, similar concept is adapted. And for tension, yes, tension is dramatically different. For normal concrete, yes, after the peak, we have some softening curve like this, but HPLCC shows the increasing of the strain and stress like this. So we adapt the trilinear line for the failure envelope like this, and we select some unloading and reloading curve. So actually, I will show in the next slide the verification of this unloading and reloading curve. But anyway, yes, we have unloading, reloading, and also due to the lateral cracking, I mean, when we have the crack orthogonally to the loading direction, we have a reduction of the strength, as I said. We develop some equation to express that effect. Means once we have a damage in lateral direction, compression and tensile strength reduces according to the damage level in lateral direction. Yes, in compression also we have. So based on the compression and tension model newly developed or newly proposed, we checked the this model applicability or accuracy. So firstly, we check the internal curve, unloading and reloading curve. To check that, we did the additional plate test where we did the cyclic loading on the plate. So apply the load, just flip, and apply the load from the other side, and we did many times. Then we could get the unloading and reloading curve of the plate. And then we did the simulation by FEM, where we install the newly developed model, and we check the two cases where the reloading curve is just straight or curved shape. So white one is the experimental result of this reversed bending test, And we found that the green one is better, means just straight curve is better result. So then we adapt this model for internal curves. Then after that, yes, we move on to the shear. For shear, also for normal concrete, we have the model. That is a function, means shear performance become 1/4 of the normal concrete because of the absence of the aggregate. When we have aggregate, we have good interlock. But in case of HPLCC, without aggregate, yes, it's easy to slip. Then shear stress is not generated so much. So actually, this value is same as a model for high-strength concrete. For reinforced concrete, when we use a high-strength concrete case, crack penetrate or break the aggregate as well because the mortar part is too strong. So that in the high-strength concrete case, also we use 25% of the normal one. So same concept is adapted for the HPLCC. And then softening model is also generated, but it's a little bit complicated. Then I do not explain in detail today. But anyway, I will go to the verification was a numerical simulation part. So firstly, we did the analysis of the plate test. Yes, the result is just a result, so that I quickly show you the result. So we could simulate exactly same loading history of the experiment like this. This is a rotated case, but anyway, white line is the experiment and yellow line is the analysis. So we could simulate the secondary loading as well. Actually, before that, we did the first loading by simulation. Then after that, yes, we change the loading condition in the simulation, then we can simulate this phenomena. Reduction of the stiffness and the strength, the tendency is well represented. Yes, this is, again, comparison. So it's actually, we could see the behavior at the bottom part by the measurement and simulation, but I skipped this part. Anyway, white one is experiment, but that one, colored one is a simulation. That shows very well. So after that, we simulate the RC panel. So yes, to confirm the behavior of the RC, because our final target is to simulate the structural scale. So what we did in the experiment was just material scale, but we want to extend it for the structural scale, so that we did the analysis for the test done at Toronto University in Canada. That was a collaborative research with Kajima Corporation Japan. But anyway, they use the ECC, HPLCC, with reinforcement. And Toronto University has a very well managed the shear panel test equipment, and where the reinforcement is same in both direction and different in X and Y direction are prepared. Totally 6 tests were done. So this is a case with same reinforcement ratio, and this is a case different reinforcement ratio. What happens in case of different ratio is that after the cracking, because of the different reinforcement ratio, an isotropic phenomena occurs after the cracking. So this is a very complex situation. Then we try to simulate these phenomena. So yes, from the experiment, we extract the tensile material property and apply this test. And this is a case with same reinforcement ratio. This is the experimental result. And yellow one is a simulation result. That agrees very well. And yes, this is the case